All right, so let's finish up what we're going to do for this week, which is section 5.4. We're going to start looking at logarithms. Does anybody remember looking at logarithms in Algebra 2? A little bit? Yeah. So logarithms are used, one use for them is just to solve a simple equation like that. Okay? Anytime you have a variable that's in the exponent and you want to solve it, that's what a log is used for. Okay, so a logarithm function is the inverse of an exponential function. So in other words, it undoes an exponential function. Kind of like squaring and square rooting undo each other or cancel each other out. It's the same idea here. So log functions have all the kind of opposite properties as exponentials. If you think of an exponential growth function as going up very quickly, while a logarithm function is going to go up very slowly. Okay? It's going to increase, but extremely slow. Okay? Just like exponentials go up extremely fast. All right, so in math, there's two different main what we call line tests. There's the vertical line test, which tells you if something is a function. But then there's the horizontal line test, which tells you not if what you're looking at is a function, but if what you're looking at, its inverse, is a function. Right? So for example, if I had a parabola, and I asked you, does that pass the vertical line test? What would you say? Jane? Yeah, it passes the vertical line test, so a parabola is a function. Well, a horizontal line test. Does a horizontal line only hit a parabola once? No. So what that means is a parabola fails the horizontal line test, so the inverse of a parabola is not a function. If you were to sketch the inverse, it would not be a function. So, exponential functions, okay, those pass the horizontal line test. Okay? If you sketch an exponential function, draw a horizontal line, no matter where you position that horizontal line, it's only going to hit the exponential one time. So, I want to try to connect the ideas here. Okay? Logarithms are the inverse of exponentials. Exponentials pass the horizontal line test. So what does that mean about logarithms? If they're the inverse of exponentials, and exponentials pass the horizontal line test. Yeah, sorry. Yeah, logarithms are functions. Exactly. Logarithms are functions. So again, just kind of put it into simple terms. What that means is something's a function. For every input, there's only one output. So if you give me a number, tell me to take the log of it, there is only one answer. And in general, not just logs or exponentials, but any function, if you want to know what the inverse looks like visually, it's a mirror image over the line y equals x. So the line y equals x goes right through the origin, has a slope of 1. It kind of cuts through the quadrants 1 and 3 on a 45-degree angle. If you mirror image something over that line, you just drew the inverse. Okay, so what I have in blue, okay, that's an exponential. In black, that's the line y equals x, going right through the origin on a 45-degree angle. In red, the calculator had a little trouble sketching it, but what it should look like is that. In red, that's a log function. And hopefully you can tell that if it's a mirror image, like if that was a piece of paper and you folded it right on the black line, the blue one and the red one would land right on top of each other. Okay, So a couple things. Notice that logarithms and exponentials both increase as you head to the right. The blue graph is going up, the red graph is going up. But the red graph is going up extremely slow. Okay? In fact, if you were to, let's start out at the log of 5. Okay? So if you go over 5 units, you're up a little bit more than a half, okay? About 0.7. If you go all the way out to 50, you've only gone up to 1.7 on the y-axis. So going out 50 units on the x only brought you up 1 more unit on the y. Okay? And even if you go like log of 1,000, going all the way out to 1,000 on the x-axis, you're only at 3 on the y-axis. So this goes up extremely slow. Any questions on the general idea of the relationship between an exponential and a log? Yep.
The progression of the log function, the function goes up. Does that stay the same, or does that change as it goes on?
You mean, does it ever stop going up?
No, like, does how fast it go up ever change?
Oh, like the
rate of it.
the rate of the slope?
Yeah. Because like looking at that, it seems like it does.
Yeah, I think, so that's getting into more of a calculus question, asking what's happening to the rate of change of the slope. I think what's happening, if I remember right, is it's going up, but it's going up at a slower and slower rate. You can see at first it goes up pretty fast, but then as you continue on, see these like horizontal segments, they're getting longer and longer. So the rate of increase is slowing down. Yeah. And the way you could figure that out is with what's called a derivative. You could actually predict, all right, if I was standing on that red line at, say, x equals 20, how steep would the spot be exactly at that spot that I'm standing on? Yep. Yep, so no, that's a good question. Yep, but the rate of change of the slope does slow down as you head to the right. Also notice here there's a vertical asymptote. So just like log functions have a horizontal asymptote, exponentials have a horizontal, logs have a vertical. As you get closer and closer to 0, like try the log of 0.01, okay, you're going negative. Okay. Log of 0.000001, you're at -7. Okay, so the closer and closer and closer you get to 0, the further down on the y-axis you go. But it's so steep that the calculator can't sketch it. That's why it looked like the graph just stopped. Okay, but it doesn't stop. That's why I added in that part. All right, so the first thing is how we pronounce an equation that has log in it. Okay, and the way you pronounce it is y equals log base a of x. If you were writing that on lined paper, it would look something like this. Log base a of x. It's not that the x is an exponent. It's that the a is below the line. An exponent would be up here, like that. Okay, so that's log base a of x. Okay, x is the thing you're plugging into the log function. Okay, and the name for the thing you plug in is called the argument. Okay, a lot of functions have arguments. They all have arguments. It's what you plug in. So like here, I could say the argument to the square root function is 8. It's the thing that the function is operating on. Right? So in this case, x is usually a number and a is usually a number if you're going to evaluate it. Okay, but again, x is called the argument and a is the base. Okay. Now, I typed in a couple problems on the calculator, log, all those different logs, and notice there's no subscript on the log. There's no base written. Well, if there's no base written, we always assume that it's what we call the common log, which is base 10. Okay, the base can be any positive number. You can't have a negative base in a log. If you do, it's going to be imaginary. Same thing with the argument. If you try to take the log of a negative number, it's going to come out imaginary. It's a non-real answer. So neither the base or the argument can be negative. If you try 0, that doesn't work either. Okay, so you've got to have a positive number for the argument in the base. Okay, so that's what I just said. If you don't see a base written, we assume that it's base 10, common log. So on the graphing calculator, or pretty much any calculator, there's only 2 logs you can type in directly. This is one of them. Okay? And there's a button right next to the number 7. Anybody know the other log? And I kind of mentioned it yesterday when we talked about E. Remember what I called that? I said E has something to do with this log. And it's not the common log, it was another name. It began with an N.
Natural logarithm.
Natural logarithm. Okay, so there's one other logarithm that the calculator can type in directly just by pressing a single button, and that's the natural logarithm. So the natural logarithm is a log with a special base, and the base is E. And yesterday we saw what E was. It's 2.718. Okay, but remember, E is it's like pi. Okay, it doesn't keep repeating 1828, 1828. It looks like it does, but it doesn't. Okay, after that it changes. And that's the natural logarithm. Now, when you have a natural logarithm, if you look at the calculator, notice the button right below log says ln. You normally never see that written, ever. Okay? So we use an abbreviation, and that's a short way of writing log base E. Okay? ln. Okay, the one thing you have to be careful about when you use the abbreviation is you have to remember what the base is. Because when you write it as ln, the base is hidden. Okay, so you have to remember that ln means natural log, which means base E. Okay, so when we do problems, anywhere we see a log base E, if we want to shorten it up, we're going to change it to ln. So if I said to you to find log base E of 6, you could shorten that by just saying find the ln of 6. And besides those logarithms, those are the only 2 you can type into the calculator directly. So I said to you, though, the base can be any positive number. It doesn't have to just be a 10 or an E. You could do log base 6. The only problem is there's no button on the calculator to do log base 6. Okay, so I'll show you how you would evaluate something on the calculator, any calculator. It doesn't have to be graphing, eventually. Okay, I'm not sure if we'll get to that today. Okay. Any question on that? So if we go back and look at the graph I showed you, the domain is 0 to infinity. You can take the log of any positive number. In the range, well, if we go back and look at the graph, the log graph, it went up and down forever. It didn't go up very fast, but it will go up forever. So the domain of your log function, 0 to infinity. Your range, negative infinity to infinity. Any question on why that's the domain and range, looking at the graph in red? All right. And again, we're assuming we want real answers. If you want imaginary, then you can take log of negative, but that's not what we're going to focus on. All right, so when you have a log problem, there's generally two ways you can write an equation. You can have an equation in what I call log form, or you can have the equation in exponential form. And a lot of times to solve, you have to change one to the other. So in the problems, or in the equation I'm about to show you, I'm assuming that the variable I'm using is a, and that a is a positive number, not equal to 1. So on the left, that's a log form. On the right, that's exponential form. So we just have to kind of learn, when you rewrite it, there's three things. We have to figure out which one goes where. Okay. First thing I usually do is, if you give me something in log form, I focus on the a, okay, what's in the blue box. A is the base on my log. When you rewrite it as an exponential, a is the base on your exponent. So that's how I remember where that one goes. All right, so that's the a. The next thing is what's in the green box. Okay, logarithms always equal exponents. So logs always equal exponents. Okay, that's what a log is. Okay. When you type in a calculation on the calculator, like log of 8, that number, 0.903, that's an exponent to something. Whatever, word problem or whatever you're doing, that number is an exponent. So logarithms are always equal to exponents. So if you remember that, whatever your logarithm equals becomes the exponent. And if you can figure out where the base goes, which is a, where the y goes, there's only one spot left. If you're going to make this an equation, that's what you'd have after you do the first two. You've got to put the third thing by itself on the other side. Okay, so we'll practice a couple changing from log to exponential and then exponential to log. So first thing, when you change it to exponential, the word log is gone. So we need an equal sign. Let's start with our base. Sam, what's my base here?
3.
3. Yep. So 3 is going to be the base. So now we need an exponent on the 3. What's going to be the exponent here? Yep. X. Let's go back and look at it. So remember, logarithms always equal what?
Y.
Exponents, right? So your log always equals your exponent.
So it's y.
Okay, and now what would have to go by itself on the other side? Gracie?
Or x, I mean.
X.
Sorry.
Yeah. Now there's nothing you can do with that to solve it further, but let's say I said y is 2. Well, if y is 2, once you rewrite it, the answer to the problem would be 3 to the second power. You just have to do it out. Okay. But in order to go further with this, you'd have to know either x or y. Any questions on? Let's try another one. Y equals log base 5 of x. Leo, what's my base there?
5.
5? Yep. So now I need an exponent on the 5. Yeah, Rebecca?
5.
Yeah. Whatever's by itself in the log equation, that's always your exponent. And the only thing you have left is the x. Any question on that one? All right. Let's try it the other way. So now we're going to take something that's exponential, and we're going to turn it into a log. All right. So first thing, okay, if we're changing it to a logarithmic expression, got to put the word log. All right. What's going to be the base on my log? Okay.
1.2.
Yeah. Whatever the base was on the exponential, that's the base on my log. Okay. And we said logarithms always equal what? They always equal the exponent. And what's the exponent in this one? 3. So the only thing I haven't used yet is the m. And what do we call what goes here, the thing that's being plugged into the log function? The argument. Exactly. That's it. So that's changing from exponential to log form. All right, let's try this one. Let's start with log. Dylan, what's my base here?
E.
Yep, e. Again, logarithms always equal the exponent. So Sam, what's my exponent here? B. And the only thing I haven't used yet is the 9. Now, that's one that we can shorten up a little bit. How could I rewrite in a shorter way what B equals? Yep, thank you. It's the ln of 9. Okay, and that's something you could plug in on the calculator if they wanted to know it. You just press ln 9. It's about 2.2. But again, we're not finding the decimal here. Okay, and let's try one more. Anyone think they can tell me the whole thing when you convert that to log form? Yep, Sam.
4 equals log a by 4.
Log.
24.
You're just missing one word in there.
Base.
Yeah, log, perfect. Log base A of 24. Okay. Any question on that one? So which form you have to change to depends on the problem. Sometimes you have to change it to log form, sometimes you change it to exponential. Usually, if you're trying to solve it, whatever form it's in, you have to change it to the other one. All right, so I want to show that log base 2 of 8 equals 3. So up to now, what's the only thing that I've shown you how to do with an equation that's in log form? Yeah? Change it to exponential. It's the only thing we know how to do, so let's do that and see if it works. So the goal here is to end up with a true statement, and that'll prove that it's correct. So Caleb, can you tell me what would be my base when I change it to log form, exponential?
Base would be what A is, so 2.
So yep, base is 2. Okay, what about my exponent? Yep, Leo?
3.
3, because the logarithm always equals the exponent. And Abby, what number haven't I used?
8.
8. I haven't used the argument. Is that true? Does 2 cubed equal 8? Yeah. So then we've shown that if you took log base 2 of 8, if you knew how to type that in on your calculator, which I haven't shown you yet, the answer would come out to 3. Yeah. Any questions on that? Let's try this one. So similar to the last one, except now I haven't told you what's on the other side. You need to figure out what would go there. So Shauna, what do you think we're going to do with that equation? Yeah, we're going to change it to exponential. Could you tell me what my base would be? Yep, your base is 5. And what about your exponent? 5. 5 to the x. And what goes on the other side? 1/25. All right, now if you get stuck solving that, think of this problem. Instead of, it's not the same answer, but it's similar in how you would think about it. Okay. If you can figure out 5 to what power is 25, you should be able to figure out 5 to what power is 1/25. What kind of number do you have to have in the exponent to cause the fraction to flip?
It would have to be a fraction exponent.
Well, fraction exponents are used when you want to take roots. Like if you put a 1/2, it would be like a square root, or a 1/3 would be a cube root. So we do use fraction exponents, but not to flip it. We use a different kind of exponent.
Negative.
A negative. Yep. So in this case, 5 to the second power would be 25. So 5 to what power would be 1/25?
Negative 2.
-2. And for now, I wouldn't give you one where this number wasn't a power of that number. Okay. Because we don't know how to type this in with base 5 on the calculator yet. Okay. Any questions on that one? All right. Let's try this one. So a little different. Last time the variable was on the right side by itself. This time the variable is in the argument. Okay, so I put the variable in a different spot. How about Tessa? What could I do to this equation? The only thing we know how to do up to this point. Yeah, let's change it to exponential. So what would your base be? 5. And your power? 1.5. And what would go on the other side? X. Yeah. So 5 to the 1.5 equals x. And now just take that in. Figure out what 5 to the 1.5 power is. Or if you're thinking of it as a fractional exponent, what that really means to do when you raise 5 to the 1.5 power means to take 5, cube it, and then take the square root. That's what a 1.5 exponent does. It cubes the 5 and then takes the square root of that result. Right. But it's just as easy to type in the decimal. And you get that. But just to show you that the other way would have worked, cube 5 and then take the square root of 125. 11.18. Any questions on that one? Right, so we did one where the variable was by itself on the right. We did one where the variable was the argument. Let's try one where the variable is the base. How about Tanya? Can you tell me how to rewrite that in exponential form?
The base is x, exponent is 2, and equals 3.
Sweet. Now how do we solve that one? X squared equals 3. Megan?
You take the square root.
Yeah, take the square root of both sides. And now when you take a square root, normally you get 2 answers. But what did I say about the base? What kind of number does the base have to be?
Positive.
It has to be positive, so you can ignore the negative square root of 3. Unless you're doing imaginaries. So there's one of each type you could have where the variable is in all the different spots. Any questions on that one? Okay. So we've looked at simplifying some simple equations. And now the last 2 things we're going to look at are some special properties of logs. All these properties I'm about to show you, anywhere you see a, I'm assuming that it's positive and not the number 1. Okay, so these properties are more like patterns to look for. There's really no calculation or arithmetic or anything you have to do. It's just a special pattern. So if you had 3 to the log base 3 of x, in other words, sorry, I'm excited about logs. If that number and that number match, like here, as long as those two things match, basically what happens is this whole part just cancels itself out. You don't cross it out in your notes because you need to read it. But that whole part cancels itself out, and the answer is whatever was sitting right there. So in this problem, that whole thing would just cancel out because the 2's match, and the answer is whatever's sitting right there. Okay, so again, there's no arithmetic to really do. It's just a special pattern. Okay. Only works if those two numbers are the same. Okay, another special pattern. Okay, that's more of an exponential pattern because you have a base to a power equals x. This one's a little different. This is a log pattern. You have log, base of something, argument of something. And same idea kind of happens is if these two things match, kind of like in this problem, if those two numbers match, this part cancels itself out, and the answer is whatever was sitting right there. Okay, let's look at why the let's get why the second one is true. So that's an equation in log form. There's three things: base, argument, thing on the other side. Let's rewrite that in exponential form without the word log and see what happens. Okay, Caleb, what's my base in number 2?
A.
Yeah, my base is right there, A. What's my, Rebecca, what's my exponent? X, right there. Logarithms always equal the exponent. So I've used the base, I used what's on the other side. The only thing I haven't used is the argument, which is a to the x. Does a to the x equal a to the x? Yeah. So what this property basically is, if you remember from geometry, it's the reflexive property. It's just not written the way you saw it in geometry, like this. Or maybe in geometry you saw it like a equals a or something. It's written as a log rule. But that's all property 2 is. It's the reflexive property written as a log. Okay, third property. It says log base a of a equals 1. So if you wanted to know log base 4 of 4, the answer is 1. Let's rewrite it and see why this one works. Okay, Gracie, what's my base here? And I'm just going to differentiate them. The one in the red box or the black box? Yeah, the base is in the black box. A. Jaden, what's my exponent?
It would be 1.
1. Logarithms always equal your exponent. And Megan, what's the only thing I haven't used? The A in, yeah, the red box. So if you rewrite that as an exponential, it says a to the first power is a. Is that true? Yeah. So what rule 3 is basically saying is if you raise anything to the first power, you get the same thing back. That's all that that's saying. Anything to the first power is itself. On the right, I wrote it as an equation just to kind of prove why it's true. On the left, it's written as a log. So you've seen all these rules before, including the last one I'm going to show you, but you've seen them as exponential. You've never probably, or maybe you haven't seen them as a log rule. So this says log base a of 1 equals 0. So in other words, the log of 1 is always 0. It doesn't matter what the base is. How would you rewrite that as an exponential? Jay?
It'd be a to the 0 power equal to 1.
Yeah. And if you raise something to the 0 power, do you always get 1? Yeah. It's another basic rule from algebra, just telling you that anything to the 0 power is 1. On the right, probably how you've seen it before. On the left, how you can write that rule with a logarithm. Right. So again, not really a lot of arithmetic or anything you'd have to do. They're just special patterns to look for. So let's try a couple problems. All right, so first, I just want to try to identify what pattern or what rule that one follows. Does anyone see on example 6a which pattern it looks like? Yeah.
First one.
Yeah, it's the first one. So if you apply that rule to example 6a, what would you get for x?
Pi.
Pi. So the answer, whenever you have something like that, those numbers are the same. The pattern is they cancel out. I didn't prove why on that one. You could go through it if you want. It ends up being a reflexive property, just like number 2. That's why rule number 1 works. It's kind of another way to write the reflexive property. But we're not going to go through that. So x is 3.14. All right, how about b? Anybody see what pattern that one fits? Yep, Rebecca.
Number 2.
Yep, that's number 2 because it's a log, and the base and the argument, match. So applying property 2 to that one, can anybody tell me what that would simplify to, Gracie? It would be -4. And again, once you know how to type that in, you could type it in. It would be a waste of time though. If you know the pattern, you can see the answer much faster than typing it in. How about example C? The ln of e to the kt. This one's a little tricky, but the pattern is there, but it's hidden. Let me see which one that fits. Leo?
Would it be 2?
Yeah, it is 2. Can you rewrite that in a way that would make it more obvious?
Log base e of e to the kt.
Perfect. You can replace ln with log base e. Okay, that's what's hidden. E to the kt. Now, it's definitely rule 2. So what would you get, or what would that simplify to?
X equals kt.
Yeah, whatever the variable is, that whole thing would simplify to k times t. If you want to put equals x, you could put that too. I didn't make one up for, let's pick either rule 3 or 4. Log base 6 of 1. What rule is that one? Yeah, Rebecca?
4.
Rule 4, and what would log base 6 of 1 equal? 0. Okay. What this is asking on the left is 6 to what power would give you 1? Well, 6 to the 0 power would give you 1. That's the answer. Okay. Any questions on that? Okay, so just some simple properties that'll help you when you get certain expressions to simplify. All right, so last group of properties is properties we can use to either take logarithms that are separate and combine them together, or the other way around. Take something that's already combined together and split it apart. Okay, and there's 3 main properties. The first one, basically, if you wanted to summarize it, says that the log of a product is equal to the sum of the logs of the factors. That's how you could simplify that. The log of a product equals the sum of the log of the individual factors. Now, I only did it for 2, m times n. But if you had m times n times x, you could add another sum onto the end of it. So it works for as many factors as you have. As many factors as you have in the parentheses, that'll dictate how many terms you have that you're summing together. So there's an example with numbers. This one I'll show you. So if I had log of 4 times 5, so log of 4 times 5, I get 1.3 roughly. And if I take the log of 4 plus the log of 5, I get the same thing. Now, I just showed this to you, and I assumed that the base was what? The way that I typed it in. Yeah. 10. It would work for any base. It's just 10 is the fastest one for me to type in. So you could do it with base 7, base 2.5, base e. So if you do it with base e, you could replace all the logs with ln's. Okay. And it always works. So the log of a product splits as a sum. How do you think the log of a quotient would split? Leo?
Subtraction.
It splits as subtraction. What's important though is you subtract the top minus the bottom. With a sum, the order you add in, not that important. With a difference, it is. Okay, I'm not going to type that one in on the calculator, but if you want to double check, you could type that in. The log of 4/5 would equal the log of 4 minus the log of 5. Again, that's just one example out of an infinite number of examples I could give you. Now, the third rule is basically rule 1 when all the factors are the same, like x times x times x, or just x times x. It's a special case when you're multiplying the same thing over and over. Okay, so let's look at that first. See if we can figure out what rule 3 is by applying rule 1. Okay, and then we'll write it down. So you might want to leave a couple lines here to put that rule in. So let's look at the log of x times x. Actually, yeah, let's do it that way. Log of x times x times x. Or you might even see it written this way. Log of x cubed. Same thing. So if you really break that down into what x cubed means, it's x times x times x. Now, if we use rule 1 on that, what did we say that a product splits as? Is that a sum or a difference? A sum. How many things would I be adding together here? 3. I would have log of the first plus log of the second plus log of the third. Okay, I just applied rule 1 to that problem. But now we can simplify that a little bit more. What's log of x plus log of x plus log of x?
3 times log of x.
3 times log of x. Okay, that's why we use multiplication. If you're going to add the same thing up over and over, that's multiplication. So that's 3 log x. Does anybody see, if you look at what we started with and what we finished with, a shortcut without having to go through the steps in the middle? Megan?
We take the exponent and add it as
Yeah.
quotient.
And that's the third rule. Okay, if you have an exponent on an argument, you are allowed to just move it to the front of the log. And the reason why I just showed you. It goes back to rule 1. Okay, and where that is going to come in handy is going to have to do with a problem like that. So if you have a square root in a log problem, remember what we said about square roots. Square roots are really hiding a 1/2 exponent. So if you had something like this, and you wrote that as a final answer, and I said to make sure you don't leave roots in the answer. Well, technically, you should write it like that. Because that square root of x is an x to the 1/2, and the 1/2 can come down in front. Okay, so anytime you write a final answer on a test, that's what you want. And the way the directions would be worded for that is it would say express powers as factors. Okay? Even hidden powers, like square roots, so that's a power. It's a hidden power. You have to put it in front. That's what a factor is, in front. All right, so what we're going to do with this one is just split it into two logs. Shauna, is that going to split as a sum or a difference? Yep, it's going to be a sum because it's multiplication. When you split it as a sum, whatever the base was to start with, that's the base when you split it. So it's both log base 4s. Dylan, what's going to be the argument to my first log?
3.
And to my second log?
X.
Perfect. That's it. So log base 4 of 3 plus log base 4 of x. All right, let's try this one. Gracie, is that one going to split as a sum or a difference? Difference would only be if you had a quotient like that. So that's going to split as a sum. It's a little more complicated than the last one, but it's still something times something. Sam, when I split it, what's going to be the base on each log? 2. Log base 2. And Jay, in my first argument? 5. And now the second argument, just watch me for a second before you write it down. Megan, what would the second argument be? It would be r cubed. But what can you do with the 3? Move it in front. And you have to do that because the direction said express powers as factors. Okay. Questions on that one? All right, let's try a quotient. So Leo, how's that quotient going to split?
It's going to be subtraction.
Subtraction. What's going to be the base on each log?
9.
9. Log base 9. And Abby, my first argument, or my argument to the first log?
Would be 2.
2 is in the bottom, so when we subtract, we got to make sure that that one comes at the end. Yep. So in this case, we would have x. So log of the top minus log of the bottom. All right. You can call this example D in your notes if you want. I'm just skipping ahead to the last one, or one that has an ln, because we haven't done one with an ln. All right. So here, first thing I see is I have a fraction. So that's the first step. I just want to split that fraction apart. Now you don't have to write log base e. You can use the abbreviation ln. But Sam, since it's a fraction, how does that split?
Subtraction.
Subtraction. Okay. And Trevor, could you tell me what my first argument would be?
X squared.
And what could you do with the 2 on the x squared?
Put it in front.
Put it in front. So I'm just going to do that all at once. 2 ln x. And Tanya, what would be my argument for my second ln?
The x minus 1.
To what power? To the third? And then what could you do with the power?
3 goes before.
3 goes before it. You do have to leave parentheses around the x minus 1, just so people understand that it's all part of the ln. Any questions on that one? All right, we'll try one more splitting, and then we'll do a couple combining, and that'll be it. I think splitting is harder because you're actually taking something that's already condensed and complicating it, rather than taking something that's separate and simplifying it. Okay, I think that way is easier. All right, so first of all, looking at that right away, do we have a quotient A product or both? We have a quotient first, but then we have a product second. So you always deal with the quotient first. So it's log of the top minus log of the bottom. Log of the top minus log of the bottom. And now, what can I do to this first part? Something hidden here that I have to remember to do. Gracie?
You cancel out the square.
When you have a binomial under a root, you can't do that. If the +1 wasn't there, you could. Yep. But what's that square root of x hiding that the direction said to take care of?
An exponent of 1/2.
An exponent of 1/2. So remember that x squared plus 1 is all to the 1/2 power. So you have to write it like that. And that's it for the first term. We don't have a rule for a sum. We have a rule for a product. We have a rule for a quotient. There's nothing we can do with a sum. Minus. And now you have the log of a product. So how does the log of a product split? Yep.
Addition.
As addition. So it would be log of x cubed, but what would I do with the 3? Yep.
Put it in front.
Put it in front. Plus, it would be log of x plus 1 to the 4th, but I'm going to put the 4 in front. Now the reason I left the brackets around that whole section is because you are subtracting all of that. So really that minus, if you wanted to do it out, is distributed to each of them. I'm not going to do it up. I'm just going to leave it like that. And that's pretty much as far as you could go. Unless you wanted to distribute the negative, that would be the very last thing that you could do. All right, so let's look at a couple where we recombine into one. So I have this separated as a sum. How would a sum recombine? Caleb?
Multiplication.
Multiplication. What would be the base when I recombine it?
Would it be 7 times 3? So
Well, the base would be, not the argument. What would the base be?
I don't know.
What's the base when it's split?
Log
A, right? So when you recombine it, the base is,
stay.
it's still A. Yeah, the base never changes. And now we're going to recombine it as a product. Something times something. What's the first something? Sam? 7. Now be careful. What would the second something be? Think about where that 4 would have been. Leo?
3 to the 4th.
It would have been 3 to the 4th. So that 4 goes back up as an exponent. All right, so that would be, let's just do that out. 7 times 3 to the 4th, 567. Okay, so that's recombining. I had one more recombining, but that's the idea. We can do more recombining tomorrow if we need to, but I think recombining is easier than splitting.
Do you have to put your answer as a single number like that?
You might end up with well, yeah, it usually ends up as a single answer. Yeah. Any questions on that? All right, so we covered a lot of stuff on logs, kind of all the basics, how you convert between log and exponential, and then all the different properties to combine and split logs. Okay, so the homework in your book, it's on 292, 1 through 7, 13 to 17, 21 to 27, and 29 to 33. Okay, I will be after school today if anybody needs extra help. Otherwise, I will see you tomorrow, and we have our first test of term 2 tomorrow.